Welcome my friends, welcome to my next lecture. Now as I said in my last lecture, so in this lecture I will talk about, in my last lecture I discussed about what is called modulus of a complex number and what is the complex conjugate. So what I will do this lecture, so I will give some kind of properties of like modulus and conjugations of complex numbers, and then I will talk about what is called, if I have a complex number, then you people are familiar with that complex number has a polar representation, right? And then it will have a what is called trigonometric representation. So a couple of things I will discuss in this lecture. So that is the overview. Like still I am actually doing like the review of complex numbers and its algebra. And then of course later on I will talk about what is topology of sets, complex number system. It will have a distance. I think today also I will discuss there is a distance concept in complex between two complex numbers. So therefore you will have a topology, and then once I will have the complex plane with topology and the algebra, then I will talk about the definition of complex valued functions of complex variable, and then we will have the properties you know in real analysis like continuity, differentiability, that I will talk about that. So as I said, today's lecture I will talk about a couple of properties. So maybe people are familiar with those properties kind of earlier, but I think it is better to recall those properties, because couple of inequalities or properties you will see that later on you need it to solve some problems. So like I have listed 13 properties, or 13 you can say as it also exercise also. Okay. So these properties, like it is a combinations of modulus and conjugate. So couple of them are very easy, and couple of them you need to do some kind of effort to solve that. Nevertheless, this one maybe I'll talk about 9 and 10. If you see this 9 and 10, these two are very useful actually to solve some of the problems. Okay, let me just discuss. So first property is very trivial, like absolute or modulus of z is always positive. So the way I have defined modulus of z, it is square root of x square plus y square if z is equal to x plus iy. So this is positive, that's okay. So this one property is trivial. Then what about property 2? It says that if I take the modulus of z bar and z, both are same, which is same as modulus of minus of z. So I am not going to prove all that kind of properties because it is actually straightforward. You just use the definitions of complex conjugate or use the definitions of modulus of a complex number, then you will do that. Okay. So again, number 3, mod z square. This is also kind of useful properties in problem solving. We will see sometimes you have to deal with what is called mod z square, but mod z square you can just write this is z times z bar, and that is okay. Then you just prove it, very easy to prove. So z is equal to say x plus iy, this is my complex number, or xy belongs to R. Then what is mod? What is modulus of z? This is square root of x square plus y square, right, by definitions. Then what is mod z square? This is x square plus y square. So left hand side turns out to be x square plus y square. Calculate the right hand side. So you have a z, okay. So what is z bar? Z bar is x minus iy, right? Then what is z times z bar? So this is x plus iy, then x minus iy. Then you just do the algebra with the fact that I square is equal to minus 1. So therefore what will happen? This is x square minus I times xy plus I times yx, then plus minus an I square. So therefore this is minus I square times y square. Now what is the properties of I square is minus 1. So therefore what will happen? You will have x square, okay. But you see x and y are real numbers. So x times y is equal to y times x, so they commute. So therefore these two terms get cancelled. So what we will have, I square is equal to minus 1, so therefore x square plus y square. So it's okay. So therefore left hand side is equal to the right hand side. So it's straightforward. So but at the same time I must say that these are the properties will be very much useful to solve problems. So you should know that, okay. Number 4 is that the absolute of z, which is dominated by mod x plus mod y, okay. It's from the definition it follows. You just look at the definitions, because mod z square, okay, you just do some manipulations. I am not going to prove it, you just complete it, okay. Okay, so this is also another nice property, is that the real part of z, if I have a complex number z which is x plus iy, real part of z absolute is dominated by the modulus of z, imaginary part of z absolute is dominated by the modulus of the z, and that's clear from this definition now. So this is x, this is y. So you can think about like mod z square, which is real part of z square plus imaginary part of z square, right? because x is the real part of z and y is the imaginary part of z. So now this is sum of two positive numbers, so therefore you can, from there you can easily say that real part of z square, which is dominated by mod z square. Okay, if I take the square out, so therefore absolute of real part of z, which is nothing but absolute of x, which is dominated by mod z, and that's what it is. Similarly for the imaginary. So these are the properties will be useful. Okay, then if I take the absolute of the product of two complex numbers z1 z2, it becomes mod z1 times mod z2. Then you will have a parallelogram law. Okay, so what is that? If I just absolute of z1 plus, if I start with two complex numbers z1 and z2, then modulus of z1 plus z2 square plus modulus of z1 minus z2 square, which is exactly 2 times mod z1 square plus mod z2 square. Okay, so again this is very trivial. What we have to do, so mod square you know, so again, so that's why I'm saying that the earlier properties will be useful to prove that. So what you will do, I'm just giving a hint. Okay, so you have a mod square, right? So z1 plus z2 is a complex number, mod square. But what is the formula for mod square? So you know it is z times z bar. So what we will have to do, so you have a z1 plus z2 times z1 plus z2 bar. You can do that. Similarly you can do that plus z1 minus z2 times z1 minus z2 bar. Okay, and then what you do, you just z1 plus z2 is there. Now z1 plus z2 whole bar, but bar will distribute, so therefore this is same as, you can say that z1 plus z2, then z1 bar plus z2 bar, individual bar, because bar will distribute. Okay, so plus z1 minus z2 times z1 bar minus z2 bar, and then just do the algebra. So then you'll end up with this kind of things. Cross term will get cancelled, so that means z1 z2 bar or z1 bar z2, this term will get cancelled. So what will remain is the 2 times z1 times z1 bar plus z2 times z2 bar, that means 2 times modulus of z1 square plus mod of z2 square. Okay, so I am not going to I'm not doing fully the proof, but you just use the definitions of bar, or in earlier properties like 1 to 6, you will be able to prove that. Okay, this is the triangle inequality, modulus of z1 plus z2, which is dominated by mod z1 plus mod z2. Again you just take z1 is equal to x1 plus i1, z2 is equal to x2 plus iy2, then z1 plus z2, you just take the absolute and you can easily prove that this is same. So this is also one kind of another triangle inequality. This is modulus of z1 minus z2. In fact, it follows from there itself. So this is very trivial. Why? Because z1 minus z2, I can write this is z1 plus of minus z2, right? Okay, and use the triangle inequality. What is that? This is mod z1 plus absolute of minus mod z2. Okay, but minus of mod z2, you see what? All mod are same. So therefore, this is less or equal to what is called mod z1 plus mod z2, and this is the same. Okay. So this is the one, maybe kind of, as I said, it will be useful to have this kind of inequalities. What it says, if I have two complex numbers z1, z2, then z1 minus z2, if I take the absolute, it is greater equal to. So it is greater equal to modulus of z1 minus modulus of z2. But again, I think if you are like triangle inequality, if I of course I have to use triangle inequality to prove that, but sometimes this inequality will be very useful. So how to do that? Now I can prove it. Okay, so you have to use triangle inequality to prove that. Okay, so let me start with what is mod z1. Okay, so what is mod z1? I can say that this is same as z1 minus z2 plus z2, because z2 will get cancelled same. Now you see, you think about, this is one complex number, this is one complex number. Okay, so now use the triangle inequality. So modulus of z1 plus z2 is less or equal to mod z1 plus mod z2. So therefore I can say that this is less or equal to mod z1 minus z2 plus mod z2. Okay, clear? So then you take mod z2 in the left hand side. So therefore you have mod z1 minus mod z2, which is less or equal to modulus of z1 minus z2. Okay, this is one. Now do the same process replacing z1 by z2, that's it. So what we have, so now you start with z2. Okay, what is that? This is z2 minus z1 plus z1. Okay, now think about, this is one complex number, this is another complex number. Again use the triangle inequality. What is that? This is z2 minus z1 plus mod z1, right? But I want that it should be modulus of z1 minus z2, but what is that? This is same as modulus of minus of z1 minus, sorry, this should be z1 minus z2 minus sign, mod plus mod z1. But modulus of the complex number is same as the modulus of the minus of the complex number. So therefore you can say that this is same as z1 minus z2 plus z1. Now you take back, so what will happen? This should be modulus of Z2 minus modulus of Z1, which is lesser or equal to modulus of Z1 minus Z2. Now this is 1 and this is 2. Now look at the equation 1 and 2. So first equation, it says that modulus of Z1 minus modulus of Z2, which is dominated by modulus of Z1 minus Z2. And what is the second one? Modulus of Z2 minus modulus of Z1. So that means this is also dominated by modulus of Z1 minus Z2. Now what is the mod of a complex number? It is a real number. So what equation 1 and equation 2 says that x is dominated by something and minus of x is also dominated by something. What does that mean? That means modulus of that number should be dominated. So therefore equation 1 and equation 2 will tell you modulus of mod Z1 minus mod Z2, which is dominated by modulus of Z1 minus Z2. Okay, and this is nothing but this one. Clear? Yeah. So this inequality also the slight similar kind, same way you can prove it 11 also. So modulus of Z1 plus Z2, which is also greater or equal to modulus of mod Z1 minus mod Z2. So these two inequalities will be very much useful to solve like many problems. So these two, again 2 and 3, that is also, and you have a parallelogram and a triangle inequality. So these are the very basic inequalities. You don't have to do anything. You just use the definitions of the modulus. You just use the definitions of the complex conjugate and play with that, just algebra. Okay. 2 is that absolute of Z1 divided by Z2, your absolute will distribute. That means it is absolute of Z1 divided by absolute of Z2, provided Z2 is non-zero. And using that properties, then if I have modulus of Z to the power n, that means I have a Z n times. If I take the absolute, then use that properties. Use property 6. That means modulus will distribute. That means modulus of Z1 times Z2 is same as mod Z1 times mod Z2. If I use this formula, I will have this one. And then if I have a minus n, then it will again be true, because if Z is non-zero, you have to use what is called properties 12. That means if Z to the power minus n, that means 1 by Z to the power n if Z is non-zero, and use this same formula, then you will do that. Okay. So these are the like couple of properties. It is not all. There are many like properties will be available, combinations of modulus and conjugate, but these are the I think that this is like if you know this kind of formulas, it will be helpful to solve problems later on. Okay, so another two inequalities. Okay, again I am not going to prove it, but maybe you need it later on. So that's why I'm just additional information, so I'm saying it. What is that? First one is the Lagrange identity, and second one is the Cauchy-Schwarz inequality. These two inequalities are like very famous inequality. Okay, so what it says that if I start with Z1, Z2, Zn in complex number, and if I have another set W1, W2, Wn are two sets of complex numbers, then what will happen? I can estimate that what is called k from 1 up to n zk times wk absolute square, which is exactly equal to, and this is, I think it is a kind of, you can easily prove it. You see that what it says that if I take the absolute in the outside, then I can put absolute in the inside the sum. Look, it is absolute in the outside the sum, right? Now look at the right hand side. Now I have absolute in the inside the sum. So therefore, how the absolute outside the sum can be, I can put it into inside the sum. So that is the like beauty of this Lagrange identity, and that's also you can do that, because you see zk and wk are complex number. So zk times wk is again a complex number. If I sum it, this is also a complex number. So altogether it is a complex number, right? And you are trying to calculate mod z square, but you know the formula. What is the formula of mod z square? For some complex number, this is z times z bar. So you just use that one, that's it. So therefore you have one complex number, and then you have to apply with the bar. So z times z bar, then you use the properties of bar, because bar will distribute, then do some algebra, then you will, and then club it, or then you can just club your term appropriately, then you will end up with this kind of things. Okay, so I'm giving a hint. Okay, so that means the idea is that, so you just write this mod square as k from 1 up to n zk wk, this is one term, times k from 1 up to n zk wk, and this time it will be bar. And then use the properties of bar. Bar will distribute in the summation, then do the algebra, then you will end up with this one. So this is the Lagrange identity. So idea is that when I can, or what is the formula to, like if I have a modulus in the outside of the summation, when do I kind of put that modulus inside the summation? So by this formula. Okay, so this is Lagrange identity. And Second one is that Cauchy-Schwarz inequality. That is a kind of wonderful inequality. In fact, it is very nice. Again, it will be useful to solve many problems. What is that? It is again like saying that it is like I have a like estimate. I want to estimate the sum of the product of the complex number in terms of the individuals. How do I do that? Okay. So what it says, if I have Z1, Z2, Zn, W1, W2, Wn are two sets of complex number, what it says that if I take the sum of the product, that means k from 1 up to n, Zk, Wk bar, absolute square which is dominated by individual, that means sum from k up to 1 up to n mod Zk square and then sum k from 1 up to n mod Wk square. So that means in some sense you can think about that. I am estimating the sum of the product of the complex number in terms of the individual. Individuals means, see, look, sum of the product means I have two sets of complex numbers Zk and Wk, right? So I am estimating this product, sum of the product by individuals, that means by Zk's and Wk's separately. Here this is actually implicit, but here in the right hand side it is explicit in terms of Zk and Wk. So that is called Cauchy-Schwarz inequality. Okay, so here of course this is inequality. What I'm another conclusion is that where the equality sign holds, that means this becomes equality if and only Zk is proportional, that means a scalar multiple of Wk for each k. If this is the case, then this inequality becomes equality. Okay, so this is called Cauchy-Schwarz inequality. So that means sum of the product I can estimate it in terms of the individual tuple Z1, Z2, Zn and W1, W2, Wn. So these two inequalities will be useful to solve problems later on. Okay, so now I come back to the again like the concept of distance, but I already discussed, because as a set complex number is nothing but the points in R2, and R2 you have a concept of distance. So now the question is, can I have the concept of distance in the context of complex plane? Answer is yes, you can do that. Okay, so like it should be automatic from the concept of distance in R2, and it is indeed the case. Okay, so let Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2 be two complex number. Then you see I have written, then the usual Euclidean distance between Z1 and Z2 is nothing but the, if I think about Z1 as x1 comma y1 as a point in R2, Z2 is x2 comma y2 as a point in R2, then what is the Euclidean distance between x1 y1 and x2 y2? This is square root of x2 minus x1 square plus y2 minus y1 square, exactly the same. So distance between Z1 minus Z2, which is nothing but this, and which is same as absolute I have defined, absolute of a complex number. So you have a complex number Z2, you have a complex number Z1, take the difference, it will be a complex number, and take the absolute. And if I calculate absolute in terms of the components, it becomes x2 minus x1 square and y2 minus y1 square. So this is the corresponding distance in the complex plane between two complex numbers. And this distance, it becomes a metric in the complex plane, and then complex plane becomes a metric space. Once I have a metric space, then I can talk about what is called topology, right? Topology means what? I can talk about open set, closed sets, limit point, closure, all kind of things, and then I can talk about the convergence of the sequences, because it has a metric. With respect to that metric, it becomes a metric space. So with respect to that distance, sometimes this is called metric. Okay, this is a distance and this is a metric. With respect to that matrix, my complex plane becomes a metric space, and then I can talk about topology or convergence or open set, closed sets. Okay, so this is one kind of geometry. So it says that, okay, so this is my, suppose I'm in a complex plane, so this is my point x1, y1, this is x2, y2, two complex number, then the distance between this to this is nothing but, so you can think about x2 minus x1, this being this side, y1 minus y2 this one, so therefore this is the one, it's nothing but square root of x2 minus x1 square plus y2 minus y1 square. So this distance, okay, like the Euclidean distance. Okay, so example, for example, if I take z1 is equal to 1 plus I, z2 is equal to 1 minus I, just use the formula z1 minus z2. What is z1 minus z2? You can easily calculate z1 minus z2. What is that? This should be 1 will get cancelled, which will have what? z1 minus z2, so 2i. Okay, so 2i means what? I is what? 0 plus, so that means you can say that is x plus iy form. That means 0 plus 2 times I. So that means what is that? Oh, acha. So okay, you can think about, say this is mod, this is mod, this is mod. So what is that? So this should be square root of 0 square plus 2 square. So that means this is 2. This is what it is. Okay. So that is the kind of usual concept of distance in a complex plane, and it is automatic and is quite natural because it is coming from the Euclidean distance in R2. Okay. So with respect to that distance or that matrix, you have this complex plane C with respect to D becomes a metric space. So as I said, once I have a metric space, then I can talk about open set, closed sets, and its convergence. This is one notation, so you can think about that. What is mod z? So mod z I can think about, this is z minus 0. So according to your formula, this is nothing but d of 0 comma z. So that means the distance from the origin to the complex plane z, which is nothing but the modulus of the z. Okay. Okay, so now as I said, so like you know, complex number has a polar decomposition, so polar form, polar representation I should say. So you see a polar form of a non-zero complex number. What is that? So that is also kind of like earlier one x y, x plus iy or x comma y, sometimes it's called as the Cartesian kind of form. So this is polar form. So what is polar form? So suppose this is my complex plane, so suppose this is real axis, this is imaginary axis, and suppose this is your complex number. Okay, now each complex number I can represent that point, instead of x comma y, I can represent that point as r comma theta. What is my r? R is that, suppose this is my point, r is the distance from the origin. Sometimes this is called the pole. Okay, so distance from the origin to that point, so I will say that this is r. And theta, what is theta? Theta is that, so once I have a kind of origin and I have a point, so this is the vector. So theta is the actually the angle from the your real axis in the anticlockwise direction to the vector OP. So therefore you have a point, suppose complex number P, so you draw a vector from the origin, so you have a vector OP. Okay, so now, so first you get the modulus, first you get the distance from the origin and the point, so I am saying that this is r, and I am saying that once I have a vector OP, then I am measuring an angle from the real axis anticlockwise directions with the vector OP, and suppose let it be theta, then I will say that the same point P, I can say that it is, I can represent that point in terms of r and theta. What is r? R is the distance from the origin to that point, and what is my theta? Theta is the angle which is measured in the anticlockwise directions from the real axis. So this is theta. So in this way I can also kind of represent a point in the complex plane. This is sometimes called polar form. Okay, so that kind of, this is the kind of connections. So this is my pole, origin is the pole, and this is my sometimes called polar axis. Suppose this is my complex number P, which I can represent as a form, instead of x comma y, I am representing as r comma theta. And what is r? R is the distance from the complex number to the pole, that means origin, this is the r. And what is my theta? Theta is the angle of the vector joining origin to the point, this vector, which makes an angle, and that angle is measured in the anticlockwise directions from the real axis or from the polar axis. So this is theta is equal to 0. So I have written here, so each non-zero complex number z, why non-zero? Because I need r, r is the distance from the origin, so therefore if z is 0, so therefore r is 0, so therefore there should not be any kind of concept of polar form. So that's why I'm saying each non-zero complex number z, xy non-zero, can be represented by the vector from the origin to the point pxy in the plane. So suppose this is my plane, so this is my point, say z is equal to x plus iy. Okay, so first origin, make a vector. Okay, so then look, the second kind of point is that the length r of the vector OP is given by the modulus. So this is the distance from the origin to the vector, so this is nothing but modulus of z, so therefore r is modulus of z, which is nothing but square root of x square plus y square, which is modulus of z. And what is my angle theta? So you see the measure theta in radians of the oriented angle from the positive real axis, so this is my positive real axis, okay, to the vector OP. So this is my vector OP, so this is my positive real axis, this is positive real axis, okay, and this is my vector OP. So what is my theta? Theta I am measuring from the positive real axis in the anti-clockwise direction to the vector OP. So that means this is the angle theta. Okay, so that's what I've written. So therefore, so the measure theta in radians of the oriented angle from the positive real axis to the vector OP is called the argument, or sometimes it's called the amplitude of the vector OP, and we write it as theta is equal to arg of z, that means argument of z. Sometimes theta is called the argument of z, not sometimes, it is called the argument of z, yes. Okay, so therefore if I have a non-zero complex number z, then I can represent my non-zero complex number as r comma theta, where r is my modulus, and what is my theta? Theta is the argument of z. I am saying theta is the argument of z, but how I can measure theta? I am measuring theta from the positive real axis in the anti-clockwise directions to the vector OP. What is my P? P is the complex number and OP is the vector joining from the origin to that point P. Okay. So this representation is called the polar representation of Z, and the values of r and theta are called the polar coordinates. So therefore, given a complex number, you will have a Cartesian coordinate x plus iy or x comma y. This is the Cartesian form, you can say. And what is the polar form? In the polar form means, so you can think about that if I have a point in the complex plane, draw a vector from the origin, and then you just get first, you get the magnitude of that vector. That means you get the distance from the origin to that point. So this is the modulus r, and you just measure the angle from the positive real axis to that vector, let it be theta, that is called the argument. So then I can represent the same complex number in the complex plane in terms of r and theta, and that is called polar representation. Once I have a polar representation, then the same complex number I can write in terms of what is called trigonometrical form. Trigonometrical form you can guess from the term trigonometry. That means I should represent my point complex, my complex number in terms of trigonometric function. That means in terms of say sine function or cosine function. Can I do that? Answer is yes, you can do that. Because you see, so just now I have discussed what is r and what is theta. So suppose this is my point, okay, this is my point in the complex plane Z. So which I can represent it as r comma theta, okay, which I can represent r comma theta. R is the distance from the origin to the point Z, and theta is the angle from positive real axis to the vector. So now if I have that one, that same point Z, if I write it as x comma y, so that means what is my x? So that means if I draw a perpendicular from here to here, this is my perpendicular, so this will be my x and this will be my y. So same point Z I can write x comma y or x plus iy. Now one hand I have a representation r comma theta, and another hand I have a Cartesian x comma y. So, but since I am drawing a perpendicular from the point P on the positive real axis, so therefore this angle is what? Pi by 2, right? 90 degree. Once I have this angle is pi by 2 and this is theta, so therefore I can write x and y in terms of r and theta, right? And what is that? If this is my r and this is my theta, what is my x? X is equal to r cosine theta and y is equal to r sine theta. That is exactly I am written. So therefore the complex number Z is equal to x plus iy, where x is equal to r cosine theta and y is equal to r sine theta. So therefore you just take r common, so therefore this is cosine theta plus I sine theta. So that is actually the representation of the same complex point in the complex plane, but this representation is known as what is called trigonometric representation. Okay. What is my theta? Theta is the argument. What is my r? R is the modulus of the complex number, and this Z I can represent as r cosine theta plus I r sine theta. And that is quite trivial, because one hand I have a Cartesian representation x comma y, and another hand I have a polar representation r comma theta. R you know, theta you know. So therefore your x by trigonometric rule, x is equal to r cosine theta, y is equal to r sine theta. So therefore r times cosine theta plus I sine theta is nothing but the trigonometric form. But there is a catch. What is that? Okay, I have written here. So from trigonometry we have cosine theta is equal to x by r, sine theta is equal to y by r by this figure. So therefore I can represent it my Z in terms of r times cosine theta plus I sine theta. So this is known as trigonometric form of a complex number Z. But there is a catch. What is that catch? You can ask this kind of question, sir, yes, Z is equal to r cosine theta plus I sine theta. So I am writing my point Z in terms of modulus and cosine function, sine functions. Okay, perfectly all right. But I know that cosine function and sine function, they are periodic functions. So therefore, the same point I can say that it is same as r of cosine of theta plus 2 pi plus I sine of theta plus 2 pi. That will also give the same value, right? Because sine and cosine are 2 pi periodic function. So therefore you can ask, so which theta I should take? So therefore if I change theta and if I perturb theta by 2 pi, the same value I will get. So therefore this is same as r of say cosine of theta plus 4 pi plus I sine theta plus 4 pi. That will also be the same. So which one I should consider? Theta plus 2 pi or theta plus say 2k pi, where k is an integer. So that is why I am saying that, see look, the number theta is determined only up to a multiple of 2 pi, and it is quite clear because both sine and cosine are periodic functions of period 2 pi, okay, and the set of all such angles is denoted by small arc. So therefore the given a complex number Z, small argument of Z is actually a set. Okay, so if I have a theta is the argument of Z, then if I perturb by 2k pi, then it is also be an argument, because I can write the same complex number in terms of cosine and sine functions, and these are 2 pi periodic functions. Okay, so look, however, all the values in the set represent the same directions in the complex plane. So that means what, in the pictorially if I see, suppose this is my complex number, okay. So suppose this is my r, this is theta, so therefore it is r cosine theta or r cosine theta comma r sine theta. Now look, so what I am doing is that instead of I am going from down here, so I am just coming full circle and then come back here. So that means, so that's the picture I am seeing. So first time I am taking this angle up to, then I am saying this one rotations of 2 pi, then again another rotation of 2 pi. So you just rotate it. So you will have the same complex number and same directions, but your argument will be a set. So you can take theta, theta plus 2 pi, theta plus 4 pi. So that's exactly I have written. However, all the values in this set represent the same directions in the complex plane. So one example I have done. So modulus, okay, modulus part is trivial, 1 plus I, you just calculate it. But what is the argument of 1 plus I? According to your formula. So if I have a, so that means this is, what is my x? So this 1 plus I, so you have a 1 plus I, right? So it is of the form x plus iy, right? So what is my x here? So my x is 1, y is 1, right? Okay. Acha. What is my r? R is the square root of x square plus y square, that means 1 plus 1, that means r is square root of 2. So now, since it is of the trigonometric form, it says that cosine theta is equal to x by r. So that means what is my cosine theta? What is my x? X is 1 by r root 2, and it will imply theta is equal to what? Pi by 4. Right? So therefore, the argument is pi by 4. That is okay. Theta, that's theta. But argument of a z, if I perturb by 2k pi, will be the same. It will give the same complex number in the also the same direction. So that is why the small arc, so small arc of 1 plus I, which is that set, that means pi by 4 plus any multiple of 2 pi. And what is the corresponding polar form? Root 2 and this pi by 4 I am saying, and similarly you will have the same, right? So pi by 4 I am just perturbed by 2 pi, again this is comma root 2 comma 9 pi by 4 and so on and so forth. So therefore, so the same point I can write it in a many ways in terms of polar form. If I perturb by theta, so each form I will get. R will be fixed because it is the modulus, this part will be fixed. The second component theta will vary, okay? And that clearly follows from this picture. So now just let me just kind of discuss this small argument, then I will talk about, so let me just complete at least this part. So what we have seen is that, so given a complex number, it will have a Cartesian form, it will have a polar form, it will have a trigonometric form. But given a complex number z, then I have defined what is called argument of z, that is called small arc. And what is small arc? Small arc is the set function. So that's what I am writing. So this is the corresponding pictures in last slide also there. So it says that for a complex number, of course, first point is that given a complex number z is equal to 0, since its modulus is 0, I am saying that argument is undefined. You cannot have the argument. Since argument is undefined because it is 0, so therefore you cannot have a polar form, so it is origin. So to talk about polar form or trigonometric form, I am saying that I need my complex number should be non-zero. Okay. So if a complex number z is written in the polar form or in the trigonometric form, then it is automatically understood that it is a non-zero complex number. So therefore, if I say that z is of the form say r comma theta or r times cosine theta plus I r times sine theta, that means it is of the trigonometric form or a polar form. If I write a complex number, automatically it is understood that my complex number is non-zero because I am talking about r, na. So if z is 0, r is 0, so therefore that does not make any sense. Okay. So therefore it is okay. Third point, what is my third point? For each non-zero z, now look, small arc of z takes a set values, I said. So it will have one argument theta, and if I have the argument theta, then if I just perturb by 2k pi, then it will again give you the same complex number. So therefore, small arc of z, so given a z complex number, small arc of z is a set values. This set is an infinite set. For each non-zero complex number z, argument function thus assigns a set value. So therefore, if I think about this function, z goes to arc, so this, you can say that this is c minus 0, okay? So it's a map, z goes to small arc of z. So each z you will have a argument of z, but it will be a set function, it is set. Okay, so that's what I'm saying. Argument function thus assigns a set value. Therefore, argument of z, you can say that it's a multiple valued functions. Okay, so given a z is a complex number, non-zero complex number corresponding to small arc of z, it is actually since it is a set, so I'm saying that z goes to small arc of z is a multi-valued function or multiple valued functions. For example, if I take argument of 5, what is argument of 5? So this is my complex plane. So this is my point 5. Okay, so what is the argument? At least what is the representation of r theta? What is the modulus? Modulus is 5, right? This is r is 5. And what is my theta? Since I am in the positive real axis, so theta is 0, right? Okay, so it is of the form 5 comma 0 r comma theta. But what is the small arc of 5? So small arc of 5. So this is theta plus 2k pi. So that means since theta is 0, so therefore it is actually 2k pi, okay, and or 2n pi I am saying, n running over z. So that's what I have written. So this is a set function. What is my set? This is 2n pi and running over z. What is argument of minus 3? Again, what is, look at the complex plane. What is minus 3? Minus 3, that means here, suppose this is minus 3. Now what is the argument? What is the modulus? Modulus is 3. What is the polar form? So this is 3 because modulus of minus 3 is same as 3. Okay. And what is my theta? Theta means this is my point, complex number. So I have to measure. So this is my vector, right? So I have to measure in the anti-clockwise direction from the positive real axis. So therefore I should start from here and come back here. So what is the angle? This is angle pi. So that means it is the polar form. This is actually theta. But what is the argument set? Argument of minus 3. This is set functions. So that means it should be pi plus 2n pi where n running over z. And this is same as what is called 2n plus 1 times pi where n running over z. And that's exactly I have written. Okay. Similarly, you can just argument of 1 plus I. What is that? First, if I just do the using the trigonometric form, the argument theta will be pi by 4, and then you just part up by 2n pi and running over z. Okay. So that means given a z, the small arc of z is a multiple valued functions, and you can explicitly calculate what is that set. So this is one exercise I have given. So argument of 5, argument of minus 3, and argument of 1 plus I have calculated. As I said, what is the corresponding set? You just calculate what is argument of 1 minus I. Okay. So you could just do it in your home. So this is all about small arc. So now in my next lecture I will talk about what is called, this is the argument. There is a concept called principal argument. That means z goes to small arc of z, it's a multivalued function or multiple valued functions. Now from the multiple valued functions, can I get a single valued functions? So that means given a z, can I associate a single argument? And that argument, is there any rule? Can I get a single valued functions out of these multiple valued functions? Answer is yes. Using that, I will define what is called principal argument for a given complex number z is non-zero. And that function will be single valued. And once I have a single valued functions, then you can talk about its continuity, differentiability, why it is defined, everything. Okay. So I think in my next lecture, I will start discussion with the principal argument. So that is principal argument, sometimes it's called capital arc. So just arguments means small arc. So small arc of z, this is the argument, it's a set functions. Then I'll come back to the concept called principal argument, that means capital arc. Then I'll say that z goes to capital arc, it's a single valued functions. Okay. So given z, you will have a unique capital arc, and then you have a unique argument theta, and that theta I am saying it is the principal argument of my complex number. Okay. I think in my next lecture I will start with that principal argument. Thank you.